we're asked to show that the floor of the square root of n plus half is always equal to the floor of square root of n minus 3 over 4 plus half, where n is a positive integer, any given positive integer. So first of all, the meaning of floor of some x that's a real number. Right? That's first of all an integer. And that integer is no larger than the number itself. But if we increase this integer by 1, somehow it's already bigger than that number. Right? For example, 2 is the floor of 2.1, no larger than 2.1. Right? Increase it by 1. 3 is already bigger than 2.1. Right? So that's the biggest integer that's no larger than the number itself. Right? That's a discrete version of Infimum and Supremum, pretty much. So I denote the floor of square root of n plus half as k. So according to the definition of floor, first of all, the floor is first of all an integer. An integer no larger than square root of n plus half. Strictly less than the floor plus 1. Then we minus half on both sides. Square root of n strictly less than k plus half. And do we know that both sides are strictly positive so that we can square both sides, maintain the direction? So it looks like n is at least 1. Right? So that's at least 1.5. Floor would be at least 1, so yes. Strictly positive, square both sides. K squared minus k plus 1 over 4 less than or equal to n, strictly less than k squared plus k plus 1 over 4. But even though k is a positive integer, but that's a decimal. Right? For example, if that's 3.25, right? But n cannot equal to 3.25, but could be equal to 3. So n is less than or equal to k squared plus k. Likewise, if that's 2.25, right, cannot equal to 2.25, right, but bigger than or equal to 2.25, but could be equal to 3. Right, 3 is just 2 plus 1, so this number plus 1, that's what I need. This one, less than or equal to. So that's the first inequality. Right? Second, I denote the floor of square root of n minus 3 over 4 plus half as n. Right? Likewise, n is at least 1, so that's at least 1 over 4. Square rooted half plus half, 1, at least 1, no problem. Positive integer. Likewise, n is no larger than square root of n minus 3 over 4 plus half. Strictly less than n plus 1. Minus half on both sides. N minus half. Less than or equal to square root of n minus 3 over 4. Strictly less than n plus half. Both sides are strictly positive. No problem. Square both sides. N squared minus n plus 1 over 4 less than or equal to n minus 3 over 4, strictly less than n squared plus m plus 1 over 4 plus 3 over 4 on both sides. M squared minus m plus 1 less than or equal to n, strictly less than m squared plus m plus 1. Like I said, this time, this is a positive integer. And so is n. But n cannot equal to that, but could equal to this minus 1. That's m squared plus m. Bigger than or equal to m squared minus m plus 1. Right? Looks like the same format. Right? Same format. Next, we prove m must equal to k. So I've denoted this floor as k, that floor as m, eventually reached these two inequalities. Same format. right? Right now we prove m must equal to k. Why? Because if I assume if k is less than m, what's going to happen? So if k is less than m, that means k cannot equal to m, but could be equal to m minus 1. Right? For example, if some unknown integer is strictly less than 9, right? Cannot equal to 9, but could be equal to 8. That's what I mean. So first of all, I use this part of the inequality. N is less than or equal to k squared plus k. Right? Following my assumption, k is less than or equal to n minus 1. So, of course, n minus 1 cannot equal to 0, right? Because k is strictly positive. So this must be also strictly positive. Right? So we replace k with n minus 1, loosening the inequality. Less than or equal to n minus 1 quantity square plus n minus 1. And what is that? That is m squared minus 2m plus m, so minus m. Plus 1 minus 1, nothing. Right? Eventually I have n is less than or equal to m squared minus m. Right, so here, what do I have? Looks like I have this, right? N is bigger than or equal to m squared minus m plus 1. What's wrong with that? Something is already wrong. I can tell, because in conclusion, n is less than or equal to m squared minus m at the same time. Bigger than or equal to m squared minus m plus 1. That's already troublesome, right? Because this bit is already bigger than the right-hand side. Exactly 1 unit bigger. For example, this 9, that is 8. How can some positive integer greater than or equal to 9 at the same time less than or equal to 8? Right? Not possible. So k cannot be less than m. Right? Now, if k is bigger than m, what's going to happen? In that case, in other words, m this time is less than k. So which means m cannot equal to k, but could be equal to k minus 1, right? The next biggest integer, right? Before k. This is possible. So what do I know? I know this time n is known to be less than or equal to m squared plus m, right? So m squared plus m. At the same time, likewise, this is definitely strictly positive. Losing the inequality, right? M less than or equal to k minus 1. This is less than or equal to k minus 1 squared plus k minus 1, right? So that is k squared minus 2k plus k minus k plus 1 minus 1, gone. Right? Likewise. And so in conclusion, here I have n not only less than or equal to k squared minus k, but also I have this. Bigger than or equal to k squared minus k plus 1. Likewise, the same reason, right? This is definitely bigger than that, right? 9 is less than or equal to some positive integer, less than or equal to 8. Right? Not possible. So k cannot be bigger than m, combined with k cannot be less than m. So k has to equal to. Right. In other words, the floor of this has to equal to the floor of